I have 20 minutes, right? I wanted my phone for... Hello, thank you for joining. I'm Ben. I only have 20 minutes, so I will not be able to go into depth of the whole project and what we've done so far and where we're going. But I want to give you an introduction of what we've been building so far. We call it Mosaic, and the problem we're directly solving is how do we scale state-rich dApps on Ethereum. As an overview, I want to focus on a mission statement and the what, and then I will go into the how, but if there's questions about the how, then I'm happy to take these also offline further and walk you through that. After the how, I can tell a bit about where we are now and where we want to go in the future. So the mission statement is to come together for a decentralized supercomputing network for humanity. Why decentralized and why a supercomputing network? Decentralized in the first place because privacy requires that you have ownership, and so we first need to construct self-custody of data, and hence in this meaning, decentralized. But why a supercomputer for humanity? What does that mean? And so as humans, we're already cyborgs. We build shoes to run better. We build planes to fly better or fly at all. But what do we build to think? The only tool we have so far are computers. And then that brings back the same question. Whose computer is it and whose thought is it? So who am I? I'm Ben. I had a life as a theoretical physicist. In 2014, I started caring about privacy, apparently enough to join a decentralized movement. But I'm here today to learn from you and to invite you on this mission. So let's try to create some context. What does it mean to have a supercomputer, right? So on this graph, you see a straight line, but it's a logarithmic scale on the y-axis. So every line, a dotted line there, is 1,000 times more operations per second. And so IBM Summit, I Googled, is, I think, the world's leading supercomputer. If you scale that down roughly a few billion times, you end up in your smartphone, in your pocket. If you scale that down 1,000 times, we have Ethereum today at roughly 500,000 operations per second. So that's not a supercomputer yet. But we don't have to be shy because mining for Ethereum has a respectable usage of computation. It's a modest supercomputer itself, but it's also highly inefficient. It's all wasted computation, and so as an observation, this graph nicely shows that probably we have built humanity's most inefficient machine ever. But we build it because we uniquely solve one problem. We construct a global state that we haven't gotten any other way to construct. And so what's the size of the problem? What's the scale of humanity? So the most powerful computer we have on this planet is the 7 billion human brains combined. And so to put that on the same graph, you end up all the way in the right top corner. And so Ethereum as a tool for humanity is a very far way off. We obviously don't have to go all the way there, but how do we build tools that support humanity better? And so what I want to present here today is that there's actually three basic well, one is not so basic because I respect them a lot, but like there's three algorithms that we know already today that really can make a significant difference on this graph for Ethereum. And the one that we will focus on here is Paralyzation. If you look at existing supercomputer systems, then you will find that the cost breakdown of having about 1 million subsystems usually is where they find a balance point. So this is a very optimistic upper bound where, say, you get 100,000x or up to a 10,000x improvement if you would parallelize different blockchains. But we're not alone in this fight. We have the fight for Ethereum 2, which is a sortition algorithm, which by itself also gives you a 1000x improvement. Theoretically speaking, they would add up, but in practice, I think it's more reasonable to say that that you would get an optimistic upper bound of twice 1,000. And then you have a third class of algorithms that are arguments of knowledge. And here I don't have a strong understanding of where the upper bound would be. So I fitted it out. But I think it's definitely feasible to think about 1000x as well. As a side note, with the Ethereum 2 work, you would also make the whole architecture far less inefficient by removing proof of work from the cost equation. So how? We have a lot of teams working on Ethereum 2, also moving away from proof of work. There's very talented teams and researchers working on arguments of knowledge. But Paralyzation, which is the foundation block for the supercomputers we have today, doesn't seem to be a conversation in the Ethereum space. And that's what I want to focus our attention on. And so how do you paralyze? So we've learned a lot how to write secure software in a parallel environment. And so what you need is an ownership model of the data. You want that only one parallel process can write to the data, but you want that many processes can read from the data. And then within Ethereum, we actually know very well how to deal with ownership. So you can have non-fungible tokens, and it's almost trivial. You can check the EIP, how to make them basically data assets to manage who can write to the data and who can only read from the data. But that by itself doesn't give you parallelization. That gives you how you write a dApp in a parallelized environment. What you also need is asynchronously parallel systems. So they need to be asynchronous because that's almost the definition of running parallel. And in a decentralized context, the asynchronicity is, of course, also important to have the security guarantees, especially when you want to have Ethereum as the hub of a hub and spoke model, which has a limited capacity. Then you cannot have any synchronous algorithm to compose the system. And so what you want to do, and this comes back to the state of dApps running on a more powerful system, is that you want to actually also compose state trees. So you want to build state trees and state transitions, and then in bulk inject them into the main Ethereum state tree. And you can actually do this with canonical BFT. So again, the proposals are very conservative. They are applying what we already learned, but now, again, add layer 2. And interestingly, I hope that this becomes clear, you can also assert data availability by sticking to canonical BFT. So that's really where we are today, right? Ethereum's main strength is that you have callable storage between contracts, but it's also its inherent weakness. We cannot have great user experience without smart contract wallets. Smart contract wallets are inherently stateful. And so there is a whole group, I've listed just some that we know, or personally know, I guess, of dApps that currently don't really have the infrastructure to function and grow, right? They have high frequency interactions, low value per transaction, and they actually want to compute on the state, which is very expensive on Ethereum right now. So continuing with the how, like how do you approach this, right? Like go out into the world and iterate. So in 2017, we built the first MVP so that we would also learn how do you build dApps in a parallel environment, but then put it on mainnet in a constrained permission form. And we're currently working on moving from generation 0 testnet to generation 1, where we would move to a permissionless system. So as a validator, you stake, and if you bring the money, you get the rights, but also the responsibilities. And then going forward, we need to architect a constitution for how to govern this as a public good. And so I want to focus a little bit deeper technically on this second point of how do you paralyze, namely how do you construct a horizontally scalable system on top of Ethereum. So imagine that you have Ethereum as it stands right now, Ethereum 1, and you now have these subsystems, and you can have an n number of them. We will call these subsystems meta chains if they satisfy these four conditions. So that's sort of the definition of what we refer to as a meta chain. What you want, and this is the crucial, one of the first problems you need to address, of course, is that you cannot burden Ethereum 1. Ethereum 1 runs on proof of work, so it has a verifier's dilemma. That means that you cannot do, you have to be inefficient on Ethereum proof of work. So you need to play a minimal consensus game on Ethereum 1 that doesn't scale with the amount of work you're finalizing, but rather scales with the number of validators in the group only. Then, as sort of emphasized already, you want that each of these systems can run and finalize their history in parallel without needing to communicate back to Ethereum 1. And this we can do because we have developed Casper FFG. And so you can use that algorithm to finalize each of these subsystems in parallel. And then you want that any of these subsystems can come back to Ethereum and commit any finalized segment of their history to Ethereum. And here the asynchronicity is important. So the asynchronicity is in the communication protocol between any subsystem and Ethereum as a hub. And then you have a unique opportunity. I'll get into that a little bit deeper, but you now can actually assert data availability. Because you have a longer time scale upon which you can actually, in the future, ask, is the data still available, and hold validators accountable for that future availability of the data. And then the fourth point is that you don't want to weaken the security. So you want that any subsystem is secured by all validators for any of the commits. Per construction, if you think of what is a block, it contains a header and it contains a transaction list. We do the same here. So you can think of a meta block in a simplified form as having a header. We call it the kernel, and the transaction list is the transition object. So it's very similar concepts. But what we do by construction is that Ethereum contracts are the ones that define the header of any new meta block. And so if you look at the diagram, those are the green arrows that are going down from Ethereum to the meta chain. And as soon as you have a new header, now any finalized history segment with Casper FFG that was running continuously on the meta chain is a correct formulation for completing a meta block. So any of these thick yellow lines, any finalized checkpoint on that history, they are a valid proposition for a meta block. And so then you have this nice opportunity to both pool the security and assert data availability. And the way that you do that is by any of these finalized checkpoints. So imagine these yellow thick lines is a finalized history of a parallel system. It's being finalized by a group of core validators, and so you can bring this aggregated signature back to Ethereum as a pre-commit. But if you know canonical BFT, then you first need to propose a block, you pre-commit to the block, and then you commit the block. And so that same sequence happens here. There's the proposal with Casper FFG, which runs continuously, of new meta blocks. And anyone can trigger this history to be pre-commit by the Ethereum contract. And what you can then do on Ethereum is post the pre-commit, generate a new committee of randomly selected validators from all validators, and they represent the full validator pool. To go back, ask if the data is available, and recompute whether it's a valid Ethereum state transition. And if so, then you commit the meta block. And then you generate a new header, you repeat the cycle. In this new header, you also have the chance to define the new validator set. So every validator, so you can join and leave per meta block. Once you have this architecture, now you can communicate between the two systems as well. So you have a fast communication channel from the hub to the meta chain, because you're continuously observing Ethereum itself. And then at every meta block that gets committed, messages that have been stored in the outbox can also be proven back on the inbox. But this is not all you get out of this construction. You actually get parallel computation, because any of the meta chains can very efficiently read any of the other meta chains. So you have one system, one parallel thread that writes, and many that read. I will keep it short. So the objective here, the next milestone, is to get to validator rewards. And have an open set where, as a validator, you need to stake to join this validator set. But most importantly, I just want to leave you with where we are now. So we are building all of this under Mosaic DAO. The contracts define the proof of stake consensus engine, which is Byzantine fault tolerant. And then we're building two validator implementations, one in Rust and one in TypeScript. And then with generation 1 and onward, we want to organize hackathons, because there's a whole talk to be had on how do you write validators in this new context. What I mean to say is that up to now, as a validator, you had a deterministic plan of attack or policy of how to contribute to the finalization. Now you have a game theoretic set of options, because with CAS-PFG, if you know, you get to choose which votes you, or you get to define your own links. And so it's actually much more interesting validator implementation, which also means that we want to create an ecosystem where we're not writing the best validator. We will try to write implementations, model implementations, but then through hackathons actually incentivize that other teams write more powerful validators that are more efficient, more resilient. And then as a statement, we want to construct this as a public good from the beginning. It was hopefully demonstrated by the fact that we're only building a small piece from the mission. And that together with the Ethereum 2 efforts and work on computational integrity algorithms, that we can actually build a tool for humanity. So if you want to talk to us, then definitely find us out here on the venue. Thank you so much for listening, and if there's any questions, you can also shoot. Thanks.
Okay, we have 2 minutes. If anyone have any questions.
Thank you. So everyone who suffered through my talk gets a free sweater, because we have them and they need to go. So thank you. Thanks.
This is a unique size or?
No, they have large, medium.
Okay.
Yeah, sorry.
Okay.